All right, let's start. So, hello everyone. Welcome to the Graphics Programming Virtual Meetup. Today we will continue talking about this book, Physically Based Rendering. We're at chapter 7 now, where we talk about uh, primitives and the intersection acceleration. So last chapter focused on shapes. So shape interface provide convenient abstraction for geometric operations like intersection and bounds. It is not sufficient to express object in a scene. We still need bind material property for each shape. So they have a like low level shape interface and a high level primitive. And yeah, PBRT CPU and GPU rendering paths is diverge on this issue. And this chapter only talk about the CPU implementation. And the GPU, they use a wavefront path tracer, so it's very different from this kind of OOP style stuff, I guess. So for the yeah, also GPU has some ray tracing APIs that can handle stuff like ray triangle intersection. So for the CPU, we have this primitive interface. And two additional primitive as aggregates, which is container that hold many primitives. This allows us to implement acceleration structures. Yeah, otherwise we need O(n) complexity of testing array against n objects. So yeah, this BVH is building a bounding value hierarchy, which is hierarchy of bounding boxes around objects in the scene. There is also KD tree, but I don't see in the table of contents. Maybe they do talk about it in this chapter. Let's see. All right, let's delve into it. Uh, so they have a primitive class. Again, they use their tagged pointer stuff, but I think this is only used on the CPU. So I don't know. But then, yeah, for the CPU, you can just use like normal polymorphism, like virtual or friend.
Yeah, the tag pointer stuff is so that it'll work on the GPU as well.
Yeah, yeah. Just for people who don't have context. The primitive interface has only three methods, which just correspond to a shape method. First, bound, which returns a bounding box. Many use for bound. The most important one is acceleration data structures. Bound. And there are two types of intersection tests. This one returns a shape interaction. This one is for like normal test, and this one is a shortcut only return true or false, used for stuff like shadows. Upon finding an intersection, the primitives intersect method are also responsible for initializing a few member variables in the surface interaction in the shape intersection that it returns. I forgot what those two struct contains though. Oh, but materials. Yeah, materials and the emissive properties because shapes don't have those. Yeah. Geometric primitives. This is a basic implementation of primitive interface that store a variety of properties that may be associated with a shape. So each geometric primitive just hold a single shape. And also description of its appearance properties, including its material, its emissive properties, participating media, and the optional alpha texture. Yeah, constructor just initialize those. And geometric primitive method just delegate to shape. Intersection also called the intersection of shape. But if an intersection is found, then we do some additional process testing against an alpha texture. The alpha texture can be thought as a scalar function over the shape surface that indicate whether a shape is actually present at each point. Yeah, for leaves. But yeah, but for intermediate alpha value that's not 0 or 1, I guess it's already says stochastic, so it's some kind of random process. The one possibility is just using a fixed threshold, but this leads to hard transitions. Another option would be to return alpha from the intersection method and leave the calling code to handle it. effectively treating the surface as partially transparent, but it will not only make primitive intersection interfaces more complex, but also place new burden on integrators. And yeah, because we are already doing a path tracing, the easy way is just use the random number. So one challenge in performing the stochastic alpha test is to generating a random is to generate a uniform random number to apply it. For given ring shape, we would like this number to be the same across multiple rounds of the system. We want it to be deterministic, which is great help for debugging. Also, it's important for different random numbers to be used for different rays. So yeah, we use some hash function or hash float. We just hash float and then pass the race data into it. And if alpha test indicate that the intersection should be ignored, then another intersection test is performed. Yeah. This additional test is important for shapes like spheres, where it may reject closest intersection, but we can have another intersection further. This recursive call requires adjusting the Tmax value. Yeah, the Tmax will be Tmax minus the previous intersection point. And yeah, if we have a valid intersection at the end, then we finalize surface interaction. Also handle the case that this intersect P also need to handle the case of alpha texture. May be necessary to consider all the intersection of the array with the shape in order to determine if there's a valid intersection. Return early when they find the intersection. they do not return geometric information, we need to perform full intersection test. Yeah, yeah, alpha make it really annoying. Yeah, this is just go back to the previous one. But I think alpha for path tracing is already a lot easier than dealing with alpha value in rasterization, which is
Yeah,
yeah,
it just makes a lot of rays fail or go different ways, and which means you need a lot more uh well, more rays to resolve it.
yeah. Yeah, it's just make code more complicated, but it's not a fundamental problem. Yeah, most objects in the scene are neither emissive nor have alpha textures. Further, only a few of them typically represent a boundary between two different types of participating media. It, it is wasteful to store null value for geometric primitive in that common case. Therefore, PBRT also provides simple primitive. So the code converting a parsed scene representation into the scene for rendering uses a simple primitive in place of geometric primitive whenever it is possible. Yeah. Yeah, also because we are doing polymorphism either way, it's good if we can just like don't need to do those kind of tests. And yeah, object instancing and primitives in motion. Yeah, we just, for example, for thing like this, it makes no sense if for every leaves we have the unique geometry. Instead, it will heavily use instancing to just duplicate a lot of geometries. So only 24 million unique triangles, but the geometric complexity is 3.1 billion triangles. Yeah, if a model consort hog with thousands of identical seeds, then we don't need to have each individual seeds. And also the ecosystem thing has like 23,000 unique plants, but only 31 unique plant models. So PBRT use 4 gig of RAM to render this thing, but if without instancing, it will be yeah, just this.
Wow.
Yeah.
I mean, I've seen the videos of a person with like 2 terabytes of RAM because they just have a server board and decided to say, hey, look at my server board with 800 slots of RAM all full up.
Interesting. I wonder what kind of thing they can do with it, like compiling C++.
My understanding is that certain data processing problems are really hard to compress, and they're like, a mile wide but an inch deep. So they have to have servers or like computers with just ungodly amounts of RAM to fit the data set because even though yeah, you could page it in from memory, it's still not like practical. But that gets into such an esoteric and, niche data programming that I'm just like, I don't even know what real domains
Yeah,
are
I don't
there like
know.
that.
I think there are like some external algorithms like just page in and deal with stuff individually and then save back to disk. But yeah, maybe some algorithms is difficult. I don't know. Transformed primitive implementation make make object instancing possible. Yeah, rather than holding a shape, it store a single primitive as well as a transform. I kind of curious of their decision of because if I design this, I will probably have all the primitives stored in a transform. So shape in the previous chapters has had rendered from an object space. If a shape is held by a transformed primitive, then the shape's notion of render in space is not the actual thing's render space. Makes sense for the shape to not be all aware of additional transformation being applied. Transformed primitives, its constructor takes a primitive and also a transformation from render space to the no, it's the primitive, the object space to the render space. Wait, mode space to what? Like primitive to render space, yeah, I think. So primitive is object space and render is like word space. Someone correct me if I say something silly.
I think I'm trying to parse like if we should expect just the verbiage in that last paragraph, if we should expect primitives to like themselves create a hierarchy of primitives? Like if you're describing instance geometry with multiple primitives,
Yeah.
it's responsible for placing them in an aggregate so that only a single primitive needs to be stored here. I'm not sure what that looks like. I'm sure there's a better.
It makes sense. It makes sense. It's a hierarchy, so yeah, it makes sense. They don't call it word space, for example, because it's not word. It's just like a higher hierarchy.
Right. Okay.
The key task of transformed primitive is to bridge between primitive interface that it implements and the primitive that it holds. If the primitive member has its own transformation, that should be interpreted as a transfer from object space to the transformed primitive coordinate system. And the complete transformation to render space require both of these transformations together. Intersect method also must account for transformation. Just we need to transform the array and then inverse transform after we get the intersect information. I guess, but it's rendered from primitive. So we want two primitives, so we need to do inverse transform first. And it's afterward we perform the transform. And animated primitive class use the animated transform in place of transform. Enables user body animation. Is this for motion blur? Animated transform class use substantially more memory than transform. The former uses 696 bytes, and the later is just two matrices, like one for the direct and one for inverse. I don't know what that is, why this is large, that large. It's worthwhile to only use animated primitive for shapes that actually are animated. Oh, I guess that's why they have this kind of hierarchy of primitive and then transformed primitive and animated primitive, is because, like, as I previously said, I will just give every primitive a transform, but yes, someone needs special treatment. They will skip past the rest of implementation of animated primitive because it's the same as transformed primitive, but only use animation, and they will not explain how animation works in this section. I think they explained in a previous section. I forget like which chapter it is, but I think we skipped that. So yeah.
But
And
sorry, but does the difference in size is described just by the implementation, right? You know, like looking at the private, there's no other members here that would increase the size of the animated primitive. So it's just sort of those.
yeah, just this.
Okay. And that's what gives it the larger footprint, right?
Yeah,
Or am I misunderstanding? Okay.
yeah, it's just this thing is large.
Yeah. Okay, cool.
So acceleration structures are one of the components at heart of any ray tracer, because without algorithms to reduce the number of unnecessary intersection tests, we will have O(n) time for each ray intersection test, but doing so is extremely wasteful for most things, since the ray pass nowhere near vast majority of primitives. So acceleration structure allow quick simultaneous rejection of group of primitives. And there has been a substantial amount of research into algorithms for reintersection acceleration. And they will have a further reading section, just like all the other chapters. So there are two main approaches to this problem: spatial subdivision and object subdivision. Spatial subdivision algorithm decompose 3D space into regions and record which primitives overlap which region. And the region may also be adaptively subdivided. And yeah, I think the main data structure for spatial subdivision are like KD tree and oct tree, but for ray tracing, the main thing is object subdivision, and we use BVH. Yeah, in object subdivision, we progressively break the object in the scene down to smaller groups of nearby objects. Yeah, both of these approaches has been quite successful at solving general problem of ray intersection, and there are no fundamental reason to prefer one over the other. But I guess in practice, there are just practical reasons. As with the transformed primitive and animated primitive classes, the intersection method for aggregates are not responsible for setting the material area light and the median information at the intersection point. Yeah, those are all set by the actual intersected primitive. Yeah, all right, we finished the part. And next time we touch this book, we will actually delve into PBH bounding value hierarchies, which we also talked a lot recently. So it's good to see how differs. Any questions before I end the recording? All right.
Just said I wasn't here. What was the BVH content that you read most recently as a
Oh,
group?
it's a series of blog posts.
Oh, yeah, okay. I've seen these. Nice. Yeah, I'm curious to see how it differs from the book implementation.
And, let's stop.